Hello, my name is Schramm. I'm teaching math, physics and computer science at the Hafen City University of Hamburg. I use Maple since the early 80s, applying resultants and coordinate bases on the computation of caustics of gravitational lenses, but this is long ago. Since then, Maple is my main tool for research and teaching. The subject of my talk is what is called rational trigonometry, a concept introduced by Norman Waldberger. I became aware of him through an article in the German Public Spiegel magazine. It was about the reinterpretation of the Babylonian cuneiform tablet Plimpton 322 as a trigonometric table. I was immediately fascinated by the power of the Babylonian hexadecimal number system and the ancient knowledge about mathematics. Looking for more material about this, I found a lot of YouTube videos of the Australian professor for mathematics, Waldberger, about a lot more subjects, especially rational trigonometry. At first I thought just another nerd proclaiming having found the golden fleece of mathematics. Since I remember from the early 80s, a guy who ran every week over our campus and tried to convince us that pi is a rational number. It was ridiculous and tragic. But not so in this case. Reading Waldberger's book, Divine Proportions, I became convinced that the concept is sound and useful. And here's my talk.
Rational trigonometry using Maple. As already stated, Norman J. Waldberger introduced concepts for trigonometry and even algebra and calculus using only rational numbers. For engineers, this makes no big difference in accuracy, but is easier to understand and avoids logical problems of infinite objects. This kind of trigonometry can be fully developed, avoiding transcendental functions like sine, cosine and tangent. The main idea follows Euclid. Square areas are more powerful than distances, and angles as linear scale on the unit circle is, without integral calculus, a very problematic concept. His solution was using quadrances as squares over distances instead of distances, and spreads instead of angles as the squared ratio of the side opposite to the spread to the hypotenuse in a rectangular triangle. This will become clear in a moment. The result is that all canonical tasks in or with triangles can be solved using simple algebra with rational numbers. If you really want to know about distances, the most complicated thing you have to do is to approximate a square root. The ideas can easily be extended to standard 3D or hyperbolic geometry and then, for instance, be applied in special relativity. Waldberger laid down this new concept of geometry in his book Divine Proportions, Rational Trigonometry to Universal Geometry in 2005. We follow his approach in his Introduction to Hyperbolic Geometry 39 as a video on YouTube. German readers can find my short summarizing paper, which is referenced in the reference section. As first task, we have to define quadrants and spread for a later use, and we have already loaded plots and plot tools and linear algebra for performing some calculations with vectors. And then I introduced two vectors, u and v, and later on another vector w and some more. And using this symbolic coordinates of the vectors, we can prove the concepts and show the validity of some definitions. At first we define the quadrants as a Maple function, just using the 2 norm, and can apply it to a vector as you see here. And this is not so special, and we awaited this result here. The spread is a little bit more subtle, and the definition for vectors is also given here as a maple function with 1 minus the scalar product of the two vectors u and v divided by the quadrances of u and v. The spread is also a concept of measurement, and so we needed a device to measure triangles and the spreads in triangles, and developed something which is like a set square or a protractor, and we can show it here. We observe that we have a nonlinear scale, and it's equal on both sides here, and it goes from 0 to 1. As an example, we showed two vectors and representing two intersecting lines, and they are given here in magenta, so we can plot them in Maple, and we plot them into a coordinate system. And we observe that the spread denoted here by the green bar is just given by the quadrants of the height in the rectangular triangle given by the projection of the vector u onto v. And it's given by the quadrants of this height h divided by the quadrants of the vector u. As a remark, we note that the spread for two perpendicular vectors is just 1, for parallel vectors is just 0, and for two vectors with an angle of 45 degrees is just 1/2. And additionally, we state that in a rectangular triangle, the two remaining spreads add up just to 1. Using our definitions for quadrants and spread, we deduce a third vector w as a difference of u and v, and are able to formulate 5 theorems which are sufficient to solve all problems with triangles. The first one is, of course, Pythagoras' theorem in terms of quadrances. It simply states that the sum of the quadrances of the two small sides is equal to the quadrants of the hypotenuse. If we put in our coordinates, we see that it's similar or equivalent to the scalar product being 0 of our two vectors. There's a beautiful geometrical proof which I found in the YouTube videos of Waldberger, and then tried to reprogram this using Maple. And the idea is to put the rectangular triangle under inspection with their two quadrances of the small sides inside a larger square. And there are then 3 other congruent triangles. And then by shifting the triangles around, one can see, since the area is maintained, that the sum of the two quadrances must be equal to the quadrants over the hypotenuse. We can start the animation and observe. The next theorem is the triple quad formula. It simply states for two parallel vectors or 3 points on a line that the sum of the quadrances of the two vectors plus the quadrants of the difference vector, all squared, is equal to 2 times the squared quadrances of the 3 vectors. If we put in our coordinates, we simply see that this is equivalent to the, let's say, to the cross product of the two vectors u and v if they are extended with a 0 z coordinate. We can look at an example for two example vectors and see for this construction, if we put in just the numbers, that the theorem holds. The third one is the so-called cross law. And it states that if we define a triangle, as here in this example, by this red vector u and this blue vector v and the difference vector w, with the appropriate quadrances q, w, q, u and q, v, then the sum of the two quadrances of u and v minus the quadrants w, all squared, is equal to 4 times the quadrants of u and v times 1 minus the spread between u and v. And this formula can be checked by putting in coordinates, as we see here. And we can also check this by putting in this example coordinates, as here, and we see that the theorem holds. In principle, it replaces in some sense the cosine law, but we remember that we don't use trig functions. The fourth law is the spread law, which replaces in some sense the sine law, but we remember we don't use trig functions. For our example triangle, it simply states that the proportions of the spreads and the quadrances of the opposite side are all equal. We can prove this by putting in our coordinates, or for our example triangle simply by putting in their values, and we see that the theorem holds. Our last theorem is the triple spread formula. It, in principle, replaces the rule for triangles that all the inner angles sum up to 180 degrees, but we don't use angles. And for our example triangle, we see this relation, and it's so that the squared sum of the spreads is just 2 times the sum of the squares of these three spreads plus 4 times the product of the 3 spreads. And we can prove this by putting in the abstract coordinates, or for our triangle, for our example triangle, just by putting in the numbers, and we see that it works. As a final application, we show the simplified determination of the height of a lighthouse, which stands, by the way, in St. Peter-Ording in Böhl, and this is a small town, a famous small town at the North Sea. Here, as typical for surveying, we measure the 2 spreads from 2 different locations which are in one line to the tower, and then we use the distance between the 2 measurement points and measure the quadrants here. Of course, in surveying, we at the moment we don't measure with the devices which we have. We measure the spreads here, but we measure the angles, of course. But maybe if this is really a good idea, one could change the measurement units to measure really spreads, or we can recalculate them from the angles given by the devices here. One remark must be made here, which I should have maybe told before, that the spread, if we have 2 intersecting lines, is in all 4 corners of the 2 intersecting lines the same. So that if we look at a triangle defined by Q3 and S1 and S2, that there would be a second possibility for S3, namely if this line here, which has the quadrants Q1, is then turned over here, so that we have a different angle S3, and we have just taken here the spread S2 with the small corner here. Computing this with a rational way in Maple is rather simple. We just put in the values for S1, S2 and Q3 here, and for the possibility of repetition of the calculations we reset here all the other values. And then we use the triple spread law and simply put it in with the definitions of the values here. The only unknown is in this case S3, so we can solve this with a Maple function and assign the first value, since, as I just explained, there are two possibilities for S3, and by inspection we find that the right one is 0.093 and so on. And using this value and putting in the spread law, we can use this to calculate Q1, the quadrants Q1 here, and this is the value of 575.7 roughly, and with this value we can go to this rectangular triangle here, knowing now S2, and we know Q1 of course, and this spread here is, as we remember, is just 1, so the spread law reads like this here: S2 over capital H is equal to 1 over the quadrants 1. And we use the solve function again and find out that the capital H quadrants is roughly 201.5. And from this we take the square root using the eval f function as an approximation, and we find that the value is 14 meters and 19.4 centimeters. This is roughly the value which you find in the documentation, maybe even in Wikipedia. We can compare this to the old-fashioned way using trigonometric function, which is of course not very much more complicated, but we have to use the concepts of transcendent functions, and to understand them fully we have to use differential calculus. So just taking the related angles alpha 1, alpha 2, and the distance between the two measurement points Q3 in small letters now, and unassigning of the values we have to compute for possible further calculations or repetition of the calculations, we can first use the sum of angles rule, and so we find the third angle alpha 3, which is the angle related to S3 here, and we can use then this angle using the sine law and finding the Q1, and then using that in this rectangular triangle the height h is just the hypotenuse times the sine of the angle alpha 2 here. And so we find a similar result. There is a slight difference because of rounding errors or cancellation of decimals. And we find this by just comparing the spreads which we calculated and measured before to the squares of the sines of the angles here, and we see that there are slight differences, and if we would make this really equal, then we would have exactly the same result. Finally, we come to a short conclusion and summary. We introduced Waldberger's consistent and systematic approach to trigonometry by using only rational numbers. The concept reminds of a concept of surveying mathematics to avoid computations of trigonometric functions wherever possible, but it's much more systematic. However, taking error propagation into account, it's an open question whether there is a real benefit. But it's easier to understand and to apply for geometrical problems and as accurate as normal engineering mathematics. It could be useful at least as didactic and methodological concept in schools before the introduction of differential calculus. Thank you for listening. If you like the concept of rational trigonometry, you can download this worksheet and find in the reference sections a lot of references for further reading, especially to the book Divine Proportions. Thank you again. Bye.